So is my screen visible?
Yes, ma'am.
Okay, so let's start with today's class and let the other students join in the meantime. So in yesterday's class, we started talking about something which is known as, sorry, state feedback. Okay, so the concept of feedback, so this is a basic concept of feedback. So basically when you have an open loop system, suppose you have a system or you have a plant which is given by this, okay, and the input to your plant is, let's say, the input to your plant is U and the output to your plant is something Y. Okay, so now, so what is the main aim of this plant is that so we know that how our output should look like. Okay, so the specifications of how the transient response of the output would look like, so these things are specified to us. Okay, so that means that we have to design the plant and the plant is given to you. So if you have the input which is provided to the plant, so according to the according to the internal combinations or the internal connections of the plant, you will get a specific output, right? And now if the output is according to the desired criteria, then very good, then we can work with a open loop system only. But in case the output of this open loop system, if it is not the same as the desired one, then what do we do is that we use a feedback mechanism. So in that case, we use a feedback mechanism, and then using this feedback we try to control the output, and we can change, because the plant is something which is constant, so we cannot play around with the parameters of the plant. Okay, so we have to design this feedback in such a way that the output which is provided by this closed loop system, that is same as the desired output. Okay, so this kind of a feedback, so this is the main concept of feedback. So the state feedback, basically it means that we can take all the state variable. So whenever we are designing or we are modeling the plant using the state space model, so what we are doing is that first of all we are selecting different state variables which are integral to the plant. Okay, so state feedback means that if you can measure and control, if you can measure all the state variables, and if you can connect all the state variables back, you can feed all the state variables back to the input, and so that you can control the output of your system. That kind of a system is known as a state. That kind of a system is known as a full state feedback. Full state feedback means all the state variables, they are being fed back to the input via some gain, so that the output of the system is according to the desired specifications. Okay, so the main aim of using this feedback is that what we can do using this. Someone has their Nishan. Okay. Okay. So the main purpose of using this feedback is that what we can do is that we can change the position of the closed loop poles according to the design of this feedback. Depending on the gain of this feedback sensor, we can specify the position of the closed loop poles of the system. Okay, so we can say that the location of the poles, that is directly related to the eigenvalues of the system. Okay, and so we have already seen that the closed loop poles of the system, that are same as the eigenvalues of the system matrix. Okay, so we can say that the location of the poles is directly related to the eigenvalues of the system, and depending on the position of the closed loop poles, obviously that would govern how the system response will look like, the dynamics of the system. Okay. So the main condition that needs to be satisfied in order to implement a full state feedback, that condition is that the system must be completely controllable. If the given system or the given plant is completely controllable, then we can implement a full state feedback. But for implementing a full state feedback, you need to measure all the state variables and then feed them back to the input. Okay, so let's say that if you have a single input, single output system and the state model is of nth order. So this is basically the state equations, right? So x dot equals to ax plus bu. This is the state equation, and y equals to cx is the output equation. Okay, so this is basically the equation which corresponds to this, to the plant. Okay, so now we have provided one feedback. So this is, let's say this is a state feedback. So this is a state feedback. Okay, so essentially you can write that the state feedback, you can express it in this form, that sigma is equals to k into x, where the value of k is a vector like this, and x is obviously the state variables of your system. So this will be the block diagram of the full state feedback. So here you have the plant, you have this some other, this is the C other gain of the system. Then the output of the plant are the state variables. So we are taking the state variables, and the state variables will act as an input to the feedback sensor, and the gain of the feedback sensor is given by K, and that the output of this feedback sensor is fed back to this system input, and accordingly you get an error signal which is given by U, which is fed back to the plant. Okay, so for the plant, the equation, the state equation is given by x dot is equals to ax plus bu. Okay, so U is basically here the plant input, and R is the system input, the input which is actually provided to your system. Okay, so from this block diagram, you can write the expression for U. So U will be equals to R minus K multiplied by X. So U is equals to minus KX plus R, right? So if you want to write the state equation for the overall feedback system, so the overall feedback system will be x dot is equals to AX plus BU. So U, we will substitute U by minus KX plus R. So this becomes equal, if you equate this, it will become A minus BK into X plus B into R. Okay, so this will be the state equation for the closed loop system. So now if you can observe, or if you can verify that the pair, this A and B matrix, if this pair is controllable, then we can say that the eigenvalues of this matrix A minus BK, they can be selected suitably, and they can be placed arbitrarily using the full state feedback. They can be placed arbitrarily means that you can specify what would be the eigenvalue of this matrix A minus BK by suitably choosing the value of K. So A is constant, A and B, these two are the things which are not in your hand. They are integral to the plant. Okay, so the only thing that you can change is this, is the feedback sensor, that is K. Okay, so if you choose the value of K in such a way that you can choose the value of K such that you can have different values of eigenvalue, the eigenvalues will be different, and those eigenvalues will be according to the given specifications. That means you can place the closed loop poles of the overall system by changing or by simply playing around with the value of this matrix K. Okay, so now let's see that, let us say that you have been given with this is a system whose signal flow graph is given, and so there are like three states of your system. So this is one state x1, this point is another state x2, and this theta dot is x3. Okay, so now so all the states here are, so x1, x2, x3, all the states are measurable, and what we are doing here is that from each state we are having a feedback path. So from x3 we have a feedback via minus kd, then from x2 you have minus k1, ki, and from x1 you have minus kf. Okay, so all these are fed back to the input, and then the overall system looks like this. Okay, so now what you have to do is that you have to adjust the feedback gains, so this kd, ki, and kf, in such a way that these conditions of the transient response are met. Okay, so the given condition is that the damping ratio will be equals to 0.8, and the settling time of the system would be equals to 0.1 second. Okay, so this is the given criteria which needs to be satisfied, and you have to satisfy this criteria. You have to adjust this feedback gains in such a way that this condition is satisfied. Okay, So how to proceed with this kind of a problem? So first of all, since the signal flow graph is given, so what you can do is that you can find out the overall gain of the system. So you can find out what will be the value of Q0 by R. Okay, so if you find out, in order to find out the overall gain of the system, you have to use the Mason's gain formula. Okay, so here you have the forward path. Basically, you have a single forward path. So this one, the gain of the forward path will be equals to 1 into 25 multiplied by 500 by S multiplied by this gain 8 by S multiplied by 4.5 by S multiplied by 1. Okay, so that means this will be 25 multiplied by 500 by S. Then you have 8 by S, 4.5 by S multiplied by 1. Okay, so this will be 4.5 into 10 to the power 5 by S cube. Okay, so then the next step is you have to write the gains of the individual loops. Okay, so the loops are there are like 1, 2, 3 and 4. There are 4 individual loops. So all the gains of those loops are, this is one gain. This is the second gain. P31 is equals to right. So these are the individual gains. Similarly, you can find out what will be the value of delta 1. So delta 1 will be equals to 1 since all the loops are touching the forward path, and the value of delta will be equals to just 1 minus P11 plus P21 plus P31 plus P41. And here we don't have any two non-touching loops, so we don't have the other terms. So this delta will come out to be 1 plus 25 by S So this is the delta. So from here you can find what would be the value of Q0 by R. So Q0 by R will be nothing but 1 by delta multiplied by P1 into delta 1. Okay. So from here you can find out this equation. Okay. So next what we'll do is that this equation, this Q0 by R, this will look like, so the expression will be 4.5 Okay, so this is the overall transfer function of your system. Okay, so now you see that this is a third order system. So that means there will be 3 poles of your system. Okay, so we can write that the generalized characteristic equation of this system will be equals to, let's say, S square plus 2 zeta omega n S plus omega n square multiplied by S plus zeta omega n. Let us say that this is the generalized form, because here also you have 2 roots of this equation and 1 root of this equation. Okay, and what you can do is that you can simply compare these 2 equations, and this value of zeta and omega n, these are already provided. So since zeta is given to be 0.8, the value of Ts is given, so Ts is equals to 4 by zeta omega n. This is equals to 0.1. So from here you can find out the value of omega n. So omega n turns out to be 50 radian per second. Okay, so once you know the value of zeta and omega n, you can simply substitute these values and you can find what would be the characteristic equation for the overall system in order to meet these time response specifications. Okay, so that means the overall characteristic equation will look like s square plus 80s plus 2500 multiplied by s plus 40. So if you just simplify this, so you will get okay. So this is the this will be the characteristic equation of your system if these two conditions are satisfied. And similarly, this is also the characteristic equation of this system. So what you can do is that you can simply equate or compare these two equations, and you see that you have three unknowns. So you can just by equating you can find out what will be the value of this KD, KI and KF. So the value of KD will turn out to be this, KI will be this and KF will be this. Okay. So here you see that since your the specifications have been provided, so using those specifications, if we can measure all the states, if all the state variables of your system are measurable and controllable, obviously, then you can design the feedback with this gains so that these two criteria, that is the value of zeta is equals to 0.8 and the value of the time, the settling time is equals to 0.1 second. These two criteria will be satisfied if you adjust the gains of the state feedback according to these values. Okay, so this is the case when you have control over all the states of your system. But then in case of a practical scenario, it is always not possible that all the states cannot be measured, or if you cannot measure all the states, then feeding them back to the system, that becomes not practically realizable. So then we need to modify the system a little bit, and we'll come to that in some time. So okay, so before that, so as I have already told, that is the full state feedback is not practical, since it is not possible to measure all the states and then feed them back. Okay. So in general, if you write so this is the expression for the state equation for the feedback system, which we had seen just earlier. So x dot is equals to a minus bk into x plus dr. Okay, so this is this expression. So now if you do a transformation, so let us say that we transform this system and we use a transformation where v is equals to px. Using this transformation, so v equals to px, so that means x will be equals to p inverse of v. So if you write the overall, if you simply substitute the value of v equals to px in the previous equation, so you will end up with an equation or end up with the state equation which looks like this. Okay, so then what you can do is that you can simply substitute this value. So previously the system matrix was given by A. Now the transformed system matrix is given by AC into V plus this matrix, this B matrix has also been transformed. So this will be equals to BC into U. Okay, and this is valid for, let us, if you have the plant model, if the plant model looks like ys by us is given by this transfer function, then for this kind of a plant model, the modified or the transformed state equation will look like this. So now if you have a system with full state feedback, so this K is my full state feedback. So that means the value of U will be equals to, U was equals to minus Kx plus R. So we can substitute the value of X. So X was equals to P inverse of B. So you will have minus K P inverse into V plus R. Okay. And let us say that we substitute the value of K P inverse, we substitute it with the vector which is Kc. So value of Kc is equals to K into P inverse. Similarly, if you write the expression of V dot, so V dot is equals to AC plus V plus BC into U. Similarly, you substitute the value of U with the previous equation. So you will end up with V dot is equals to, so this will be for the overall feedback. This is the transformed state equation for the feedback system. Okay, so in the feedback system, you have AC minus BC Kc multiplied by V plus BC into R. So as we already know that if you have if you transform a state model from using some linear transformation, the eigenvalues of the system or the state model, it doesn't change. Okay, so that means the eigenvalues which was there in the previous case, that is A minus Bk before the transformation, that will be same as the eigenvalues of the transformed system, that is AC minus Bc into Kc. So these two eigenvalues will be same. Okay. Now let's say that using this this kind of a feedback, what we want to do is that we have a desired set of eigenvalues. So desired set of eigenvalues means desired set of, so this will be desired closed loop poles. If you have this, if you know this desired lambda I or the eigenvalues, then the corresponding, or you can say the corresponding characteristic equation will look like something like this, where alpha 1, alpha 2, alpha n are different constants. Okay. So then let us say that if we select the value of Kc, if we say that the elements of Kc are given by K1, K2 till Kn, so we can simply write the expression for AC minus Bc into Kc, this matrix. So AC is given by this, Bc is this matrix, and you have Kc, which is this. So you can simply do this calculation and you will end up with a matrix which looks like this. Okay, so this is in the controllable in the phase variable form or the controllable form of expression for the state equation. So now what our main aim is that we have to choose the value of Kc such that the state equation which is given by V dot is equals to ACV plus BC into U. This is in a controllable state variable form. Okay, so the state equation for that expression will look something like this. Right, so this is the state equation of the feedback system which is expressed in controllable phase variable form. Now if you compare this equation with this system matrix with the matrix given over here, so AC minus Kc into Bc, so if you compare those two, then you can say, or before comparing, so you can say that the value of K1 will be equals to alpha n minus An, K2 will be equals to alpha n minus 1 An minus 1, and Kn is equals to alpha 1 minus A1. Okay, and since we have designed this Kc in such a way that this is in a controllable phase variable form, so we can say that the characteristic equation of this system matrix should be the same as the desired characteristic equation, because this characteristic equation basically is consists of the factors which is given, or the components of the feedback sensor, that is Kc. Right, the components of the feedback sensor Kc are provided in this system matrix, right, and this is my desired system matrix. Okay, so you can simply compare those two matrices and you can find out the values of K1 till Kn. So you can write that the Kc will look like something like this. The elements of Kc will be K1 is equals to alpha n minus An, then K2 will be equals to alpha n minus 1 minus An minus 1, and so on and so forth. So now Kc is known to us, and our main aim is that we have to find out the value of K, right? So basically, if you go back to the system, you see that K is basically the feedback sensor or the feedback gain that is provided. So we have to find out the value of K, and K is equals to, and we have already seen that K will be equals to Kc into P. Kc is also known to us, so we have found out the value of Kc using this the given criteria. Okay, so we can find out the required vector K, that is the feedback vector K, just by multiplying Kc with P, and this P matrix is basically given by a matrix which is it is expressed in this form. Okay, so we'll not go into the with the details of how this P matrix is being derived, so that will take a lot of time, so we'll not go into that details. So here you can just simply find out the value of P in terms of P1. So P1 is given by this matrix, so you can say P1 is equals to 0 0 0 till 1, and you have QC inverse. So you can find out the value of P1, and from P1 you can find the value of P, and similarly you can backtrace, and you can, if you know the value of Kc, you just simply multiply Kc with P and you will find out what will be the required state feedback of the system. Okay, so now you can say that your system, if your system is completely controllable, only in that case the eigenvalues of the system can be arbitrarily located by using complete state feedback. Okay, so if your system is not completely controllable, then you cannot use this full state feedback. So using a state feedback, what you can do is that even if your open loop system is an unstable system, so you can make that system stable by particularly choosing different values of the closed loop poles in order to make the overall system stable. Okay, so any unstable open loop system can be made stable by using a complete state feedback if and only if all the states of the system are controllable. If this condition is satisfied, then we can choose the state feedback in such a way, the state feedback gains in such a way that you can make an unstable open loop system into a stable closed loop system. So that means that you can place the eigenvalues of the system at particular positions in order to make the overall system stable, or in order to satisfy some given criteria for the output of the system. So now let's try to do an example. So let us say that an open loop system is provided to you. Okay, and this is the state equation of the open loop system. Okay, so now what you have to do is that you have to design a state feedback in such a way that the transient response specification, that is zeta is equals to 0.5 and omega n is equals to 2 radian per second. These two criteria are satisfied. Okay. So the first thing to do while designing a full state feedback is that you have to check whether the system is completely controllable or not. So the first step is that, so first step is to check the controllability of the system, that is controllability of the matrix pair A, B. This A, B are known to you. So you can find out the controllability by using that Kalman's test. So you can find out the value of QC. So QC is given by matrix B, then AB, then A square B, right? So if you find out the value of this QC, so you will see that QC is given by, if you do the calculation, you will get 10. Okay, so now you see that the rank of this QC is equals to 3, and 3 is basically, that is equals to n, the nth order of the order of the system. So that means the system is, so this implies that the system is completely controllable. Now, once you have known that the system is completely controllable, so that means you can find out what would be the you can design a state feedback according to the given specifications. Okay, so for the open loop system, so for the open loop system, you can write the characteristic equation. So the characteristic equation will be lambda I minus A is equals to 0, where lambda are the eigenvalues of the system. Okay, so you can simply write, so this will be equals to lambda cube plus 11 lambda square plus 11 lambda is equals to 0. So this is the open loop, this is the characteristic equation of the open loop system. Now the given specification is that the value of zeta should be equals to 0.5 and omega is equals to 2 radian per second. Okay, so that means that so you can say that the location of the desired closed loop poles, and this is, since this is a third order, so that means there will be 3 closed loop poles. So the 3 closed loop poles, so 2 of the closed loop poles will be, so if you write the dominant one, so if you remember, this is given by minus zeta omega n plus minus j into omega n square root of 1 minus zeta square, and these values are known to you, so you can find out the pair of complex poles. So the complex poles will be minus 1 plus minus j 1.732. So out for these 2 criteria, so there will be a pair of complex conjugate poles. The position of the complex conjugate poles can be found out from these 2 criteria. Okay, So now you have a third pole also, because it's a third order system, so you will have 3 poles. So now what will be the third position of the third pole? So now since the system is an underdamped system, so that means so since the value of zeta is less than 1, so this is an underdamped system. So that means the complex conjugate poles are the dominant poles. So the complex conjugate poles, that is SD, are the dominant poles. Okay, so if this SD are the dominant poles, that means you have to place the third pole at such a position that it is not such that this dominance criteria is satisfied. Now, if you remember, when we talked about dominant pole approximation, at that time, we have seen that if the value of beta by alpha is greater than 10, where alpha is basically the real part of the dominant pole and beta is the real part of the other pole, then in order to satisfy this criteria, you can say that the third pole of the system should be placed at a value, let's say S less than equals to 10 times of zeta omega n. So zeta omega n is the real part of the complex conjugate poles. So if you place the third pole much farther into the left half plane, so the value of S is less than equals to 10 zeta omega n. In that case, this dominant pole criteria will be satisfied. So now let's place the third pole S3 at, let's say, minus 10 zeta omega n. Okay, so 10 zeta omega n is nothing but minus 10. So we have found out what will be the 3 poles of your system. So the other poles were minus 1 plus minus j 1.732. So these are the 3 closed loop poles of the system. Okay, so once you know the 3 closed loop poles of your system, so what you can do is that you can find out the denominator of the closed loop transfer function. Right, so the denominator of the closed loop transfer function will be simply S plus 10 multiplied by S plus 1 plus j 1.732 multiplied by S plus 1 minus j 1.732, right? And this will be written like this. Okay, so this is so in order to satisfy the given criteria, that is the value of zeta and omega n, so these will be the position of the closed loop poles and this will be the characteristic equation of the closed loop system. Okay, so this is the characteristic equation, means you can simply write this equation in terms of eigenvalues also. So in terms of eigenvalues, you can write that the desired closed loop characteristic equation will be lambda cube plus 12 lambda square plus 24 lambda plus 40 is equals to 0. Right, and you can also express this in the general form. So that means the general form is lambda cube plus alpha 1 lambda square alpha 2 lambda plus alpha 3 is equals to 0. So that means you can find out what will be the value of alpha 1, alpha 2 and alpha 3. Okay, and in order to find out the value of Kc, we need to know what is the value of A1, A2, A3, these also. Okay, so A1, A2, A3 are basically the constants of the open loop system. So the characteristic equation of the open loop system is written by this. So lambda cube plus 11 lambda square plus 11 lambda. So you can also write this equation in this term. So this will be plus A1 lambda square plus A2 lambda plus A3 equals to 0. Right, so from this equation, by comparing, you can find out what will be the value of A1, A2, A3, and from this equation you can find out what will be alpha 1, alpha 2 and alpha 3. So once you know, so then you can simply write the equation for Kc. So Kc will be equals to alpha 3 minus A3, then alpha 2 minus A2 and alpha 1 minus A1, right? So this is equals to 40, 13 and 1. Okay, so now once you have found out this value of Kc, then the next step is that you have to find out what is the value of P. So you have to find out what is the value of P. So before finding the value of P, you need to find out the value of P1. So once you know the value of P1, you can simply find out what is the value of P, and you can find out what will be the value of K by simply multiplying Kc with P. Okay. So once you have found out the value of P1. So P1, if you see, P1 is given by this expression. So P1 will be, this is QC inverse multiplied by this matrix. So once you know P1, so you can compute this matrix P, and then you simply multiply Kc with P, and you will get the required state feedback that is necessary for the given specifications. Okay. So then if you do like this, then you will find the value of K will be equals to, K is given by 4, 1.2 and 0.1. So that means that if you have if all the states of this system are available for measurement and controlling purpose, so that means that if the state feedback, the gains of the state feedback, if you adjust them in this way, that is 4, 1.2 and 0.1, in this way you can, if you adjust the gain in this way, then the given criteria, that is the value of zeta and omega and whatever is given in your system, those criteria will be satisfied, and you can get a satisfactory or the desired response of your system. Okay, so clear till now? Do you have any doubts till now?
No, ma'am, clearly.
Okay, so next we'll talk about something which is known as state observers. So basically, as I have already told, that you know that the complete state feedback is not always practically feasible. If it is possible, then it's very good. But in case it is not practically feasible, then we use something which is known as state observers. Okay, so before going into state observers, so from the feedback block diagram, we have seen that the control law which needs to be satisfied in order for placing the poles by state feedback is that U, the value of U should be equals to minus Kx plus R. Okay, but for implementation of this control law, what we need is that we have to feedback all the states of the system. And since this is not practically possible, let's say that in your system only you have access to the inputs of your system and the outputs of your system. Okay, so in that case, what we would do, can we implement a state feedback in that kind of a system? Yes, we can. And we use a device which is known as a state observer. Okay, so the state observer, basically it is a device whose output will approximate the state vector. Since we don't know the value of this x, the state vector x properly, so we use a state observer in order to find out an approximated value of this state variable or the state vector, and then using that approximated value, we then implement the feedback control law and then make the closed loop system. Okay, so in this case, you see, so if you see the block diagram of the feedback mechanism of the feedback system using the state observer, so you can say that basically, since we are estimating the value of x, so that means the state equations of the state observer would be the same as that of the plant. Ideally, it should be similar. Okay, so the input to the state observer will be the actual input to the plant. So one input will be U, and since we are trying to we don't have information about the state variables. So what we'll do is that we use the output of the system, and using the input and the output of the systems, we will try to approximate or estimate what will be the value of this state vector. Okay, so that means the observer should have the same state equations as the original system, and the design criteria is that we should be able to minimize the difference between the system output, that is C into X, and the output y hat is equals to C hat. Y hat is equals to C into X hat. Okay, so that means this is equivalent. If we want to minimize this output, the difference between these two, so this is equivalent to minimization of this vector x minus x hat, right? And since this x hat since this x is not accessible to us, we don't know what is the value of x. So what we'll do is that we will attempt to minimize this y minus y hat. Okay, so while implementing this state observer, what we do is that we multiply this y minus y bar, this y hat, this vector with a n cross 1 vector g. So g is basically the property or the state observer that we are designing, and then we feed it into the integrator of the observer. So the main criteria or the design problem is that we have to design the gain, this G, this matrix G, in such a way that this y minus y hat is minimized. Okay, so if this is minimized, so that means we will approximate this x minus x hat, this will be close to 0. So that means this approximation, so if this is, so if x minus x hat is approximately equals to 0, then we can write that x hat will be approximately equals to x. So if this criteria is satisfied, or if this function is minimized, then we can say that the approximation or the optimization will be much more accurate. Okay, so then from the state block diagram of the state feedback, so this is the main plant that you have. So this is the input to the plant B, and this is the plant that you have. So this part is the open loop part. So that is, you have x is equals to, x dot is equals to ax plus bu. Okay, and then you have, so this will be your this is the observer that you have, and this is the gain G, another matrix G, which you have to find out in order to minimize the function x minus x hat. Okay, so from this block diagram you can write that x hat dot will be equals to, you see that b into u plus a into x hat plus g multiplied by the difference between y minus y hat. So y minus y hat is equals to y is equals to cx, and y hat is equals to cx hat. So you can simply write this equation, you can rearrange the terms, and you will end up with x hat dot is equals to a minus gc into x hat plus gcx plus bu, right? And we already know that x dot is equals to ax plus bu. So if we take a difference of these two equations, you will end up with x dot minus x hat dot is equals to a minus gc into x minus x hat. Now if you define this x minus x hat with another vector which is x tilde, then you can write, so x tilde dot will be equals to a minus gc multiplied by x tilde. Okay, so now if this, so our main aim is that this should be equals to 0, or it should be minimal, or it should be as close as possible to 0. Okay, so that means that you can, this vector x tilde can be made to decay fast, or it can be made to reach 0 if the eigenvalues of this matrix A minus GC, if they are properly selected. So if you select the eigenvalues of this matrix in such a way that this vector x tilde, it goes to 0 very fast, then your state observer, then the overall system or the state observer that you have designed, that will be a proper selection. Okay. So in order to design this state observer, what we need to do is that first of all we have to find out. So here you see that we have the matrix A and the matrix C. Okay, so the main criteria that needs to be satisfied is that the pair, this matrix pair A and C, it should be completely observable. Okay, so now if your matrix A and C, if this matrix pair is completely observable, then you say that the eigenvalues of this A minus GC, this matrix can be chosen arbitrarily according to my requirement. It can be chosen in such a way that the value of this x tilde, that goes down to 0 very fast. Okay, so similarly, so if this pair AC is observable, then we can use the property of the duality property, and then we can write that for the pair AC, if it is observable, it implies that the pair A transpose C transpose will be controllable. So this is according to the duality property of controllability and observability. Okay, similarly, you can write if the pair AC is observable, it implies that the pair A transpose C transpose is controllable. Now the eigenvalues of this matrix A transpose minus C transpose G transpose, this can be arbitrarily chosen. Okay, it can be arbitrarily chosen because here you have this matrix A minus GC. Okay, so if you simply replace the values of, in the initial case we had A, B and K. So the main, so when we had full state feedback. So in that case we had seen, so this matrix was A minus BK. So this X dot was equals to A minus BK into X plus B into R. Okay, so here in this equation you can simply substitute the value of A, B and K with A transpose, C transpose and G transpose. If you do this if you replace these values, then if the system is completely observable, then you can find out the values of this eigenvalues of this matrix A transpose minus C transpose G transpose, and this eigenvalues of this matrix will be same as that of the matrix A minus GC transpose, or it will be similar to the matrix A minus GC, and A minus GC is nothing but this form. Okay, so depending on whether you have, so you have to choose the value of you have to choose the value of G in such a way that you can place the eigenvalues of this matrix A minus GC or this matrix A transpose minus C transpose G transpose, and you have to select the eigenvalues in such a way that the difference between the output of the state observer and the actual state variables, that is the estimation or the estimation of the state variables that is done by the state observer, that is a proper estimation, or that is a very accurate estimation. That means the difference between X minus X bar, so X minus X hat should be approximately equals to 0. You have to choose G and you have to choose the eigenvalues of A minus GC in such a way that this condition is satisfied. Okay, so that is our main criteria. Okay, so let us say that if you have been given with an open loop system. Okay, so the open loop system, that is the state equation of the open loop system, is given by this, and this is the output equation. Okay, so now we have to implement a state observer for this system. So here we actually don't know that we don't have access to all the state observer, to all the state variables that are present in our system. So in the previous case, when we were doing that, when we dealt with that other problem, so in this case actually what happened is that we already knew what will be, so we had access to all the states of the system. So we could measure all the states of the system, and accordingly we can, depending on the given criteria, we can develop or we can design the feedback of the system. But this is for a system where all the states are measurable and we are implementing a full state feedback. Okay, but in case, obviously in practical case, that is not possible. So this is an example of that practical case where you do not have, we do not have access to all the state variables. So if we do not have access to all the state variables, that means that we cannot implement a complete state feedback. Okay, so we have to develop a state observer, and we have to design a state observer for this kind of a system. Okay, and the given criteria is that the eigenvalues of the matrix A minus GC should be at one should be at -4, the other two should be -3 plus minus J1. Okay, so in order to find, or in order to design a state observer, so the first criteria that we need to check is that whether the system is completely observable or not. So the first step is to check whether the system is completely observable or not. If the system is completely observable, then we can design a state observer. If it is not, then obviously we won't be able to design a state observer for this kind of a system. Okay, so in order to find out this whether this is completely observable or not, so what we do is that we have to find out the value of this composite matrix Q0. So Q0 is given by C transpose, then you have A transpose C transpose, then you have A transpose square C transpose, right? So this is your matrix A, this is the matrix B, and this is the matrix C. So you know the value of A and C, so you can find out what will be this matrix Q0. So Q0 will come out to be 0. So I'm not actually showing you how to do the calculations. I think you would be able to do it because that will take a lot of time. So you can just simply take the transpose and do matrix multiplication, and you will end up with, you will find out what will be the value of these individual components. So I'm just writing those values. So this is the matrix Q0. Okay, so now if you see that the rank of this matrix Q0 or QO is basically equals to 3, which is nothing but which is equals to n. So that means the system is observable. So once we have observable. So once you have verified that the system is observable, then we can move to the next step and we can find out what would be the, we can design the state observer according to the given specifications. Okay, so now let us say that the eigenvalues, since the eigenvalues are given, so let's say that the value of the state observer is G, so this is given by, so we have to find out G2 and G3. Okay, so we have to find out what are the values of G1, G2 and G3. Okay, so what we need to do is that we have to find out the values or the eigenvalues of A minus GC matrix and then equate those eigenvalues with the given values, and then if you equate those, you will find out what will be the value of G1, G2 and G3. So you can simply write GC will be equals to G1, G2, G3 multiplied by C. C is 0, 0, 1. Right, so GC will be equals to okay, so GC is known, A is also known, so you can simply write what will be the value of A minus GC. So A minus GC is 1, 3. So this matrix is known to you. So what you can simply do is that you can find out what will be the eigenvalues of this matrix. So in order to find out the eigenvalues, you need to write the characteristic equation. So the characteristic equation of this system will be lambda I minus A minus GC. Determinant of this should be equals to 0. So since you have to find out the characteristic equation of this matrix, eigenvalues of this matrix, so this is the characteristic equation. You can simply substitute the values of this. So this matrix lambda I minus A minus GC. So this matrix is equals to, you have lambda minus 1, minus 3, 0. Right, so then the determinant of this matrix, so if you write determinant of this matrix should be equals to 0. So you can simply find out the determinant, and once you, so the determinant will look like, so from here you can write the equation, so lambda cube okay, so this is the desired characteristic equation for this one, and you can simply find out if you know the value of G1, G2 and G3, you can solve them and you can find out the eigenvalues. But the eigenvalues are already provided to you, right? So that means you can write that the desired characteristic equation will be equals to lambda plus 4 multiplied by lambda plus 3 plus J1 lambda plus 3 minus J1. Okay, this equals to 0. So if you expand this equation, you will end up with lambda cube plus 10 lambda square. Okay, so this is the desired characteristic equation and this is the characteristic equation which you have found from the system. So you can simply compare these two equations. By comparing these two equations, you will get the values of G1, G2 and G3. Okay, so G1 is basically equals to 25.2, G2 is equals to 21.5, and G3 is equals to 10. Okay, so that means that in this way, if your system is completely observable, then given the criteria of your system, you can find out how the state observer, that is the value of G, will depend on in order to satisfy the given criteria of your system. And when we are dealing with a state observer, so the state observer is basically generated, or the state observer is designed when all the states of your system is not accessible, or you cannot measure all the systems of your you cannot measure all the state variables of your system. Okay, in that case we will design a state observer. So in this case actually the eigenvalues are given. In some other case, some other criteria could have also been satisfied, that let's say that you have to find out the value of zeta and omega n. If those things are given, accordingly you have to change the method, and so the steps will remain same, but how you are comparing the so at the end of the day, you have to compare the desired characteristic equation with the equation that you are getting from the given state model. And once you compare those two equations, you can find out what would be the value of the state observer that you are designing for the system. So that's all from my side today. So in case if you have any doubts, you can ask now, and we'll continue in tomorrow's class.
No, ma'am, it's clear, ma'am. Ma'am, I wanted to discuss with you once the quiz date, ma'am.
Yes, the quiz, we will have the quiz on Tuesday only. Okay, so I'll post it in the group. So the quiz will be on Tuesday from 5:30.
Yes, ma'am.
Okay.
Thank you, ma'am.
Okay, so but the other thing, another thing is that like the next quizzes that we have, since we don't have much time, so please don't request us to change the dates of the last remaining two quizzes. So whenever we declare the quiz, please try to give the quiz on that date, because in this one it was okay, we could have postponed it, but now since we don't have much time left into the semester, so it might not be possible to reschedule the upcoming quizzes. Okay,
Ma'am, we'll try to do that, because we'll also having a stack of quizzes at
yes,
ending. So we'll try, ma'am. We'll try our level.
Yes, because all your other subjects will also be having the quizzes right now,
Yes,
because
the quizzes will be having for that class.
So anyways, you have to give the quizzes. Otherwise, what will happen is that you have to give quizzes on the weekends. In case we can't fit it during the weekdays, then your weekends will be gone. So try not to do that. So
yes, ma'am.
At least for this quiz, we'll have it on Tuesday. I'll post it in the group just for your reference.
Yes, okay, ma'am. Thank you.
Okay. Thank you, everyone.